Differential privacy is one of the most promising ideas in privacy engineering, but it is also one of the easiest to misunderstand because it sounds like a single feature you can turn on. In reality, differential privacy is a way of designing data analysis so that the output reveals useful patterns about a group without revealing much about any one individual. The central promise is about limiting what can be learned about a specific person from the results, even if an attacker knows a lot of other information. For beginners, it helps to treat differential privacy as a discipline for producing safer analytics, not as a label you can attach to any dataset. Using it wisely means understanding what problem it solves, what it does not solve, and how it fits into a pipeline where data is collected, processed, queried, and shared. This episode is about building a practical intuition when differential privacy is a good fit, how it is used at a high level, and what mistakes cause teams to overclaim protection. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at Cyber.Author.me in the Bare Metal Study Guide series. A good starting point is to understand why ordinary analytics can leak personal information. Even when a report only shows totals or averages, an attacker can sometimes learn about an individual by comparing results across queries. For example, if a system lets someone ask how many people in a small group have a certain attribute, and then ask the same question after removing one person from the group, the difference can reveal the person's attribute. This kind of attack is not science fiction. It is a natural consequence of allowing flexible queries on detailed data. Differential privacy addresses this by adding carefully controlled randomness so that small changes in the input, like adding or removing one person, do not strongly change the output. That makes it much harder to use the output to learn about individuals. The key point is that differential privacy is about query outputs, not about making raw data safe to share freely. The word differential highlights the idea of comparing two worlds, one where a particular person's data is included and one where it is not. A good differential privacy design makes the outputs from those two worlds very similar, so no one can confidently tell whether the person was included. That is what gives the protection meaning, because it does not rely on secrecy about who is in the dataset. In practice, this protection is achieved by injecting noise into the results or by limiting what can be asked. The noise is not random in a careless way. It is chosen based on the type of query so that overall patterns remain accurate while individual influence is obscured. Beginners should remember this. Differential privacy is a mathematical promise about limiting individual impact on outputs, and that promise depends on careful design choices. If you add arbitrary noise without a plan, you are not doing differential privacy in a meaningful sense. One of the first practical considerations is whether differential privacy is appropriate for your analytics goal. It is best suited for questions about populations, like how many users used a feature, what the average performance was, or how behavior changes across broad segments. It is less suited for tasks that require individual-level tracking, such as debugging a single person's experience or providing personalized recommendations. Differential privacy can also struggle when you need very fine-grained breakdowns, like counts for many tiny groups, because protecting individuals in small groups requires more noise, which can make results less useful. Using differential privacy wisely means selecting analytics questions that can tolerate small uncertainty and still provide value. If your stakeholders demand exact counts for very small segments, you may need a different approach, like restricting access, using larger group sizes, or avoiding that analysis entirely. The point is to match the privacy method to the analytic need rather than forcing it into an incompatible job. A central concept in differential privacy is the privacy budget, which is a way of managing how much information leakage is allowed across many queries. Even if each individual query is protected, many queries together can gradually reveal more, especially if they overlap or are adaptive. The privacy budget sets a limit on how much querying can occur before protection degrades beyond an acceptable threshold. For a beginner, it is enough to think of the privacy budget as a bank account of privacy risk, where each query spends some amount. If you spend too much, you can no longer claim strong protection, So the system needs rules about limiting queries, combining queries, or increasing noise as more queries are made. A wise pipeline treats privacy budget management as a first-class operational concern, not a theoretical footnote. If you ignore the budget and allow unlimited querying, your differential privacy story will not stand up to scrutiny. Another practical idea is sensitivity, which describes how much a single individual can change the result of a query. If one person can change a count by one, that is a certain sensitivity, but if one person can have an extreme value that changes an average a lot, sensitivity is higher. Differential privacy mechanisms often depend on bounding sensitivity, which is a fancy way of saying you limit how extreme any one person's contribution can be. In real pipelines, this might mean clipping values, limiting how many records per person are included, or defining contribution rules so one person cannot dominate. Without these bounds, noise cannot be calibrated properly, and protection can weaken. This is a place where wisdom shows up. Differential privacy is not only about adding noise at the end, it is also about shaping the input so individuals have limited influence. If you skip contribution bounding, you can end up adding lots of noise and still not achieving meaningful privacy protection. Differential privacy also interacts with the design of the pipeline itself, especially where noise is applied and where raw data is handled. A key rule of thumb is that differential privacy protects outputs, but the pipeline still needs strong security and access controls for raw data. If raw data is broadly accessible, or if teams can run non-private queries on the same dataset, differential privacy will not save you. Wise use means placing differential privacy mechanisms at controlled boundaries, like a reporting layer or a query service, and preventing bypass. It also means separating roles so that most users and most teams can only see differentially private outputs, while only a small, tightly controlled group can access raw data for operational needs. If everyone can see raw data, differential privacy becomes more of a marketing choice than a real control. Privacy engineering treats it as an architecture choice. You design the system so private outputs are the default and raw access is exceptional. Another common pitfall is misunderstanding what differential privacy does not protect. It does not prevent conclusions about groups, and it does not prevent someone from learning that a population has a certain trend. If the true population signal is strong, the differentially private output will still show it, which is the point of the method. This means differential privacy does not stop all harm, especially if the harm comes from how group-level conclusions are used. For example, if a decision discriminates against a neighborhood based on aggregated data, differential privacy might protect individuals but still enable the decision. Wise use requires thinking about downstream use and fairness, not only individual privacy. It also does not fix problems of data quality, bias, or missingness. It simply limits individual exposure. Beginners should keep this balanced view. Differential privacy is powerful for limiting individual re-identification risk in analytics outputs, but it is not a full ethics solution and not a substitute for good governance. Differential privacy also needs careful communication because it is easy to overstate. Saying data is differentially private can be misleading if you mean only some reports are, or only some queries are protected, or only under certain budget limits. A defensible claim describes what outputs are protected, under what conditions, and what risks remain. It also avoids implying that raw data was anonymized or that the organization can share everything safely. Wise teams document which metrics use differential privacy, how segmentation is handled, and how privacy budgets are enforced. They also build monitoring so they can detect when queries are approaching budget limits and when results become too noisy to be reliable. Overclaiming protection creates trust problems, especially when analysts discover that some dashboards are exact while others are noisy. Transparency and consistency are what make the approach sustainable. There is also a practical tension between utility and privacy, because adding noise can reduce accuracy. Wise use of differential privacy means choosing the right level of noise for the decision being supported. If a metric is used for a high-stakes decision, you might need larger group sizes or more conservative segmentation so accuracy remains acceptable. If a metric is used for rough trend tracking, you can tolerate more noise. It also means you avoid using differentially private outputs for tasks they are not suited for, like investigating specific user complaints or measuring tiny experimental groups. Another wise habit is to design metrics that are robust to noise, like focusing on larger cohorts and stable measures rather than on rare events. The goal is to design analytics questions that remain meaningful under privacy protection instead of treating privacy as an after-the-fact degradation. When you build differential privacy into a pipeline, you also need to consider how results will be combined and interpreted. Analysts often join datasets, create derived metrics, and build dashboards that mix multiple sources. If some sources are protected and others are not, the combined result can leak more than expected. Even within protected outputs, repeated releases of the same metric over time can allow averaging that reduces noise, which can weaken protection if not budgeted properly. Wise pipeline design accounts for repeated releases and defines how frequently outputs are published. It also controls the granularity of time series data, because daily releases for small groups can be as revealing as direct access. Beginners do not need all the math, but they should understand the basic pattern. Repeated, detailed outputs can accumulate into privacy loss. Managing that accumulation is part of what makes differential privacy real. Using differential privacy wisely is ultimately about combining a strong idea with disciplined system design. You choose analytics questions that are about groups and can tolerate some uncertainty, and you enforce contribution limits so individuals cannot dominate results. You apply privacy mechanisms at controlled boundaries and manage privacy budgets so protection does not degrade silently across many queries. You keep raw data secure and prevent bypass, and you communicate clearly about what is protected and what is not. You also remember that differential privacy protects individuals and analytics outputs, but it does not automatically solve fairness or prevent harmful group-level use. When those pieces come together, differential privacy becomes a practical tool for learning from data while respecting people, and it stands up much better when someone asks what you promised and how you made that promise real.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.